So now we are starting our second lecture on deep neural networks. In the previous lecture, we showed that deep neural networks can implement any binary function, f01n to 01m. But we also mentioned that deep neural networks are universal approximators, which means that they can implement approximately any function f from Rn to Rm if you want to approximate over a bounded region. So today, first we'll show that this indeed can be done by neural networks, and then we'll continue our study of the neural networks further. First, we consider function f from R to R. So let this function be some general function from R to R. So there I have plotted fx as a function of x. It can be discontinuous, but we will assume that it's piecewise continuous function, and we want to approximate on interval from a0 to ar. So it will be a bounded interval. We divide this interval a0 to ar in equal intervals of length delta. So now this overall interval becomes a0 to a1, a2, then all the way to ar. And we will approximate this function f by this piecewise constant function f hat, and this approximation is given by the red quantity. So therefore, f from 0 to a0 to ar during this interval will be approximated by f hat given by the red line. So this f hat is a piecewise constant function. If I take this interval delta to be small, then this approximation is going to be a good approximation. Taking delta smaller and smaller will give better and better approximation. Now, I pick just one interval ai to ai plus 1 in this and consider this function. So which I have plotted here, ai to ai plus 1. Its value during this time is fai. We are going to implement this function first via neural network. First, we define function, threshold function taix is equal to 1 if x is greater than or equal to ai. Ai is there, and equal to 0 otherwise. This can be implemented from our sine function that we have defined in the last lecture, and you can easily see that taix is this function. So therefore, we can implement taix from the sine function and simply by the neural network that way. And now this function that we have given here is implemented via a neural network given here. X enters as the input here. This is the input layer. Then TAI and TAI plus 1 are two boxes of neural networks, each one implemented this way. And then they are multiplied by FAI and minus FAI summed, and the output here will be this function FAI. This red function that you have, F hat, can be seen as summation of this kind of functions FAI. You can, if you write it as fi, so f hat is summation of fi's for I is equal to 0 to r minus 1. And now you can see that this function given, the neural network given here, implements this f hat where x is coming at the input. These boxes f sa0 to sar minus 1 are the boxes given here. And summation of them gives f hat x. As I mentioned earlier, that by taking delta smaller and smaller, we can approximate f by f hat as closely as we wish, and any f hat given here is implemented by the neural networks. So this way we have shown how one function f, any function, p may be piecewise continuous from R to R can be implemented via neural network. Now, a general function f from Rn to Rr can be implemented by the above method. What we do is just like function fr to r, we have divided the x interval over interval sublength delta. In Rn, we divide the bounded region over which we want to approximate the function into small rectangles of dimension n and represent f and by an f hat, which is piecewise constant function from Rn to R. And then each one of those approximated function, piecewise constant function, can be implemented by DNN as we have explained above for FR to R. So once we can implement this approximately via neural network, finally we come to f function from Rn to Rm. Now this function can be written as fx equal to f1x, f2x to fmx. So f is basically made up of m functions of type Rn to R. And each of fi, we have explained here, can be implemented by a neural network. So this overall function can be implemented by m such neural networks. So thus we have shown that any function piecewise continuous from Rm to Rm can be approximately as closely as we wish by a neural network. If this function f, so we are taking a bounded interval from -1 to 1, n to -1 to n, m. If it is Lipschitz continuous, then we can show we can approximate this function by a deep neural network, which requires exponential polynomial n number of nodes to approximate for each m is equal to 1. So basically, you may need an exponential number of nodes to implement a Lipschitz continuous function. The other methods that we have been talking about, k nearest neighbor, kernel methods, and random forest, also have the universal approximation capability in the sense they can also approximately implement any function from Rn to Rm. So what we have shown here for deep neural networks holds even for that. In that sense, all these methods are equivalent, but as we go along, we'll see more advantages of deep neural networks compared to these. And in fact, in the last lecture, some of those advantages we have already mentioned. Also, the neural networks that we have implemented today for any f from Rn to Rm are actually shallow neural networks. They have one hidden layer. Therefore, not just deep neural networks can approximate any function, even shallow neural networks can approximate arbitrarily closely any function of this type. We make some further comments on deep neural networks. So we mentioned that, several activation functions that we gave in the last class. Those are among the popular ones. But now ReLU or leaky ReLU have become more popular. One of the reasons is that ReLU as well as leaky ReLU is piecewise linear and convex as compared to other function that we said. Therefore, it can implement any convex or linear function more efficiently than the other activation functions that we studied. And since most general piecewise continuous functions can be better approximated by convex and linear functions than, for example, piecewise constant function that we uh, took above. Therefore, if we use ReLU activation function, it can actually more efficiently implement these functions from Rn to Rm. And this is one of the reasons ReLU has become more popular than the other activation functions. Another thing is, even though we mentioned that even shallow networks are universal approximators, but actually it has been found that deep neural networks are more efficient than the shallow neural networks in approximation of these functions. For one thing, deep neural networks can emulate a shallow neural network efficiently. Therefore, any function that can be implemented by a shallow network can be also efficiently implemented by deep neural networks. But the converse is not true in the sense that there are functions which can be efficiently implemented by deep neural networks, but cannot be that efficiently implemented by the shallow networks, can require exponentially more number of parameters. Therefore, deep neural networks are more powerful than the shallow neural networks, and therefore these are the ones which are being used today. Depth of a deep neural networks is the number of hidden layers in the network. And as I mentioned, that deep neural networks are more powerful than shallow neural networks. Even among deep neural networks, depth matters. And therefore, it is an important parameter of a deep neural network. For example, one of the okay things about deep, if the depth is more, we can show that some functions can be approximated with fewer number of parameters, and the parameters here are the number of nodes in the network and the number of edges. So it can be shown that some functions can be much better, much more approximately um, implemented on a deep neural network with higher depth than deep neural networks with less depth. Another thing is the generalization error. Now, what is generalization error? As we are going to discuss later on, the deep neural networks are supposed to approximate some functions. For example, they are supposed to provide a classifier or a regressor for some applications. To use them as a classifier, for example, and one application like face recognition system. This is a very popular application of classification via deep neural network. Now you have to make the deep neural network learn about which classes it needs to classify. And we are going to be talking about that as we go along here. Now this learning is done via providing the deep neural network with a certain number of training sequence. Now, when the learning is being done using the training sequence, the performance of the deep neural network, for example, the number of errors in the classifier that you obtain, may be lower than once it is trained and then implemented in practice in the field outside. So the performance or the error of the neural network after the training sequence on other samples, for example, other images for face recognition, is called generalization error of the deep neural network. Usually, it's the generalization error, which is the error that you obtain after it has learned and is being deployed in the field. This generalization error is usually higher than the error that you see when the deep neural network is trained on a training sequence. This generalization error can be shown that it decreases as m raised to a minus alpha, where alpha is a positive parameter close to zero, much less than half, as the number m of the training data samples is increased. Therefore, if we are using more sample to train the neural network, the performance of the resulting neural network afterwards decreases, and it decreases as m raised to a minus alpha. Not only that, this generalization error decreases as the number of parameters. The parameters are the number of nodes, and the number of edges in the network increases. So, which means that deep neural networks do not suffer from overfitting. Now, this is unlike the previous methods that we have seen, the SVM as well as the random forest and so on. In those methods, if you increase the number of parameters in the model, then you can suffer with what is called overfitting. What is overfitting can be explained by an example, simple example that everyone is familiar with. So suppose this is some data, which data I have denoted here by these points. This is a data as function of observation X. Maybe you have obtained this data from experiments, from the fields, and you want to fit a curve on this. So if you fit this curve, this blue curve, which passes through exactly each point here, then this is called overfitting. Certainly, as you are familiar with the curve fitting, this will not be a good curve fitting for this data, because as you will bring in, as you will check this curve on newer data, which is not here, this may most likely will provide a bad fitting. While this, a smoother curve given by red, is the usual curve fitting uh, curve that one expects that represents this phenomenon better. So this is called overfitting, while this is called the proper curve fitting. So what we are saying here is, in the context of machine learning, if you have more and more parameters in the model, then there is always, for a given training sample, there is always a issue of that what you learned in the machine learning from the data may actually provide overfitting, and therefore it will later on provide generalization error, which is actually worse than you would get from a curve like this. So what is seen is, unlike random forest and other SVM kind of methods, if you use more and more parameters, the learned machine will suffer from overfitting, but it doesn't happen in case of deep neural networks. This is another advantage of deep neural networks. And often, in fact, in practice, when you use deep neural networks, uh, the number of parameters used are very, very large, and the chances of overfitting would be uh, large if we were using other methods. But this problem doesn't arise in the deep neural networks. Also, the generalization error of deep neural network increases with corrupted data. What it means is, if the data has errors, noise because of bias or some error in making measurements and so on. If you have more corrupted data, then the resulting, if you use that for training sequence, the resulting machine learned that you obtain will have more generalization error. Another thing is that DNNs are biased towards simple functions. So if your actual application where the functions are, you know, supposed to be like, for example, in a classifier, the classifier function which takes data X to map into the classes, if that function is simpler, then the DNNs can provide a better approximation, a better learned system than if that the classifier function, the actual underlying classifier function, is a complex function. Now we have been talking about learning for DNNs, so we discussed that here. Learning for DNN. Basically, you start with a deep neural network with a fixed architecture. That means the number of nodes in this are fixed, the layers, number of layers, these are fixed, the edges from which node to which node there is a connected edge that is fixed, as well as the activation function that you have fixed. For example, you might be using sign function, or you might be using relu, which is the more common, or leaky relu. These are the more common activation functions. So you fix all this beforehand. And using this, you want to have a classifier for certain application. Now, the only thing left in the neural network now is the weights. The weights that you want to assign to different edges. These are going to be learned from the data. Now, if we vary the weights, the input-output function from input X to output Y is going to vary. And the appropriate weights is what we have to learn from a given data. For example, if the DNN is going to be designed to serve as a classifier or a regressor for some application, you could be maybe doing face recognition, for example, that is a classifier problem. So the learning of the deep neural network will be, we have fixed V, E, and sigma, and the thing that you are going to be varying is the set of weights, W. And you are going to be initially having a training data set, X1, Y1 to Xn, Yn. We call this overall training sample. Xi are the observations. For example, in this case, if we were taking a face recognition problem, face recognition in an image, X will be the image, and the corresponding Y that we have is the name of the person. So if I have X1, Y1 to Xn, Yn training data, that means I have X1 to Xn n images given to me, and corresponding to each one of these images, there is the name of the person which is photographed in that image. So Xi is an image which has the photo of person Yi. So these are given to us as a training data. And given this, we want to implement the deep neural network, train the deep neural networks, in other words, get the weights once these parameters are fixed, so that the classifier that we will obtain will be able to classify among those possible images of the persons. And if a new image comes later on, you need to classify from the neural network. And that classification you should be able to do properly with minimal error. So this is how it will be done by adjusting the weights W appropriately. So again, let's just take the example of face recognition thing, or as a classifier, it could be recognizing objects in an image. The objects could be, so we a priori fix the objects we are considering. It can be a table, it can be a chair, it can be cat, it can be human being, male, female, and so on. So you a priori fix the classes in which this possible object in an image will be there. And once a new image comes with one of these objects in it, one or multiple of these objects, the deep neural network should be able to identify what object or multiple objects are there in the image. And for that, we have to train the neural networks. So as I said, in this case, for object recognition, xi are the images, xi given here are the images, and y are the objects in those. So y1 is the object or multiple objects in x1 and so on. So we are given the sample s x1, y1 to xn, yn to train the deep neural network. For that, we have to obtain the appropriate set of weights. Given set of weights w, fw is going to present a mapping from the input xi to output yi. So we are, for given set f, we are going to denote it fw xi, the output of this neural network. And given the training sequence, so we do have corresponding to this xi, the label, actual label yi. So if I fix w, fwxi is the output of that neural network, and we compare that output with the actual label yi of this image xi. Now, so this label we compare with this via what is we call a loss function. And we obviously want W so that this loss function will be minimized. What is this loss function? Loss function we have to choose appropriately so that minimizing this loss function to get the W will provide us the appropriate neural network, which will do a good job for our application. So the different kind of loss function that people use are, for example, if you have classifier, then for a given W, fwxi is the class that you are going to obtain from the deep neural network corresponding to this W. You compare that with the actual label xi. We can choose a loss function such that it is equal to 0 if the neural network is classifying xi as the same object that its corresponding actual yi is. So we'll pick a loss so that this is equal to 0 if fwxi is equal to yi, and it is equal to 1 if fwi, the class given by fw of xi, is different from the actual class of xi. Okay, so this for classification, this is an appropriate loss function. We have n samples. For all the n samples for given w, we compute this quantity 1 by n, sigma I is equal to 1 to n, L fwxi yi. So this gives, for the above loss function, the fraction of training data in error if the weight set w is chosen. In case we are using this deep neural network as a regressor, what it means here is if xi and xi are the observations, y are the corresponding labels, if these are related to each other as y is equal to m naught xi plus zi, we are given xi and we are given yi, and we do not know the function m naught, and zi are some independent noise. So the aim here is to estimate the unknown function m naught given xi yi I is equal to 1 to n. Zi noise in the observations is independent of xi, and one common distribution for this is normal distribution with mean 0 and variance sigma. So if this is the regression problem, then we will try to get W, which minimizes the loss function given by this. Here, loss between FWXI for given W and YI is taken as a norm between FWXI minus YI. And norm, there are multiple norms. So I have written one L. L is a non-negative integer. Common L's are L is equal to 1. So if L is equal to 1, then this norm is given where as if this y is the output have m parameters is given by summation j is equal to 1 to I mod of yi prime j minus yij. So this is the norm of yi prime minus yi between these two vectors for L is equal to 1. If we take L is equal to 2, this is L2 norm, then this is defined as summation j is equal to 1 to m yi prime j minus yij mod of the difference square summation over all components and then take a square root. So this is the usual L2 norm. So for the regression problem, the loss between the output of the neural network for xi and the actual label yi is given by one of these possible things. And after we have chosen the appropriate loss function, the aim of learning in the machine learning for DNN is going to be via the training data. If we are given the training x1, y1 to xn, yn, is to find W, which minimizes this function. Sigma I is equal to 1 to n L fw xi yi divided by 1 by n. This is called the empirical risk corresponding to W for this training data. So learning of DNN is actually an optimization problem in which we try to get the W, which minimizes the loss function given here for a given training data. Instead of this loss function, one can also consider a modification of it. So we take and try to minimize this function. This is the empirical loss function, and we add to that another parameter, lambda into L2 norm of the weight vector W, where lambda is a positive fixed parameter. This is called regularized empirical risk. So instead of minimizing empirical risk, one could possibly minimize this find W, which will minimize the regularized empirical risk. There are definite advantages of using regularization function compared to the empirical risk. Of course, There are trade-offs in choosing what lambda you choose. If lambda you choose is equal to 0, then this is same as minimization of empirical risk. If lambda is positive, then of course there are different possibilities. If we take lambda to be very large, then in minimization, second component is given much more emphasis, and the optimal solution will be such that the second component will be low, while possibly the first component, the empirical risk component, can be large. So therefore, which of course you don't want. Therefore, lambda has to be chosen appropriately, not too small and not too large. This optimization problem, whether of empirical risk minimization or regularized empirical risk minimization, is actually a non-convex optimization problem. And this is known to be a challenging problem in optimization theory. And this is one of the issues that one has to address when studying deep neural networks. We'll continue our study of learning deep neural networks in next video. Thank you very much.